Okay, welcome to the revision of the Electrotechnology N3 August 2024 paper. So it's a full paper revision that we want to do. Okay, so for the sake of time and progress, I will not go through the the instructions. I'll just go straight to the questions. Okay, question number one, they saying indicate whether the following statements are true or false by writing only true or false next to the question number. So it's 1.1 to 1.10. Let's start with 1.1. They saying the transformer consists of primary and secondary windings which are electrically connected. So the key term there is electrically connected, because indeed a transformer consists of primary and secondary windings, but are they electrically connected? What is an electrical connection? It's a connection that includes conductors. So the primary and the secondary, apparently they are not connected by conductors, rather they are magnetically connected. So that's a false statement there. That's false, right? So that's false, right? Let's go to the next question. Delta connection is one of the methods used to connect three-phase loads. Apparently that's true. Indeed, delta connection together with the star connection, it's one of the methods that are used to connect three-phase loads. So that's true. Let's go to the next question. Three-phase network has two operating voltages known as phase voltage and line voltage, and indeed that's true. Those are the two operating voltages on three-phase voltages. Power factor is the ratio of apparent power to true power. So in the exam, it's very, very important again to understand the questions. It's a ratio of apparent power to true power. Apparently, it's not true because it is actually the opposite. It is a ratio of true power to apparent power, not apparent power to true power. So that's false then. That's false. 1.4, 1.5, the function of the logic gate is to complete or interrupt circuits. Apparently that's true. That's true. Right. 1.6, the armature consists of two laminated plates which are insulated from each other with varnish. That's not correct. It's false there. Okay. Then the purpose of the commutator in a direct current motor is to ensure that a steady direct voltage is obtained from the alternating EMF generated in the rotating conductors. So that's true. That's what the commutator is actually serving. It's for reversal of the direction. 1.8, shunt motors produce a very high starting and operating torque. That's not correct. They don't do that. Actually, they do the opposite. So a motor converts mechanical energy to electrical energy. That's not a motor. That's not what a motor does. Actually, that's a generator which does that. Power factor correction is achieved by installing the induction motor. That's not correct. Power factor correction is actually done by the synchronous motor, not the induction. And also we can use phase advancers. So that's not true there. False. Okay, let's go to the next question. The next question is saying, name two variables that are that the torque is directly proportional to. Torque is directly proportional to IA, the armature current, and phi, the flux. So those two are armature current. So we just write them. Armature current, and what else? And the flux per pole. We call it the flux, the magnetic flux per pole. Right. That's phi. That's its symbol there. IA is the symbol for armature current. Okay, let's go to the next question. State Faraday's law of electromagnetic induction. Okay, it states that an EMF or an open circuit voltage is induced in the coil whenever the magnetic flux linking with the coil changes. Or we can say an EMF is induced in a coil or conductor when the coil or conductor is cut by a magnetic field. That's Faraday's law there, 2.2. Let's go to 2.1. Name two methods used to control the speed of the DC motor, right? We can vary the value of the armature voltage, or we can vary the value of the main magnetic flux. These are some of the ways that we can actually change the speed of we use to control actually the speed of the DC motor. Okay, we can also, so we are saying we can vary the value of the main magnetic flux, and we can vary also the effective number of armature conductors. Then we can use what is called the word Leonard control system, right? We'll learn more about it in the levels that are coming ahead, together with calculations. Also, the series parallel speed control. That's another one again. So we have the series parallel speed control, word Leonard control system, varying the effective number of armature conductors, varying the value of the magnetic flux, varying the value of the armature voltage. These are methods, more than two actually, that we can use to control the speed of the DC motor. Okay, let's go to 2.4. A series motor draws 45 amperes from the voltage from a 250 volt supply. The resistance of the series field and the armature are 0.1 and 0.25 respectively. Respectively means in that order, of course. So we know that this is our shunt and this is going to be our, so this is our series and this is our RA, the series resistance and the armature resistance. Determine the motor constant if it runs at 1000 revolts per minute and the useful flux per pole is 25 milliwebers. To calculate the motor constant, it's from the formula E is equals to K multiplied by N times phi. So it's K and phi, where we have the motor constant. So making K the subject, it means if we divide by N phi both sides, we end up having K is equals to E over N times phi, right? So do we have E? No, apparently we do not have it, but it's a series motor. So it means it's possible then to calculate the EMF, the back EMF of the motor. So what are we going to do? Right. Let's then calculate it. E is equal to, since it's a motor V, the terminal voltage minus, apparently that the terminal voltage becomes our main voltage, our EMF, our main voltage in the circuit. So it's going to be given by V minus IA RA minus IA R series. Right, so IA R series minus IRA, it's not a problem because these are now potential differences together with the back EMF that we are looking for. Right, so substituting what we have. So apparently IA, since the series machine, remember everything is in series. So we have the armature, the armature, it's in series with the field, and therefore IL will be equal to I series will be equal to IA, right? So that's what we have there. Okay, so let's perform then the calculation. Right, so I'm just going to calculate it here quickly. Right, so we are saying, what is our V, the terminal voltage? That's 250 there from the information we have, minus what is our IA, that's our IL as well, which is 45, multiplied by our RA, which we have been given as 0.25. Right, so the order that we've been given there, minus 45 again, multiplied by 0.1, marking our R series. Right, so we just punch this on the calculator and we are going to get 234.25 volts. That marks our back EMF. Hence, we can now use that formula we had created there. K is equal to E over N times phi, right? So substituting that, 234.25 divided by N, the number of tens, that's 1,000 revs we've been given there per minute, multiplied by the flux per pole, 25 milli. So since it's 25 milliwebers, that's millis times 10 to the power of -3. So simply say 25 multiplied by 10 to the power of negative what? -3. And that will give us 9.37. That marks our constant, the motor constant. Okay, so basically this is what is happening. Let's quickly go to the next question. Okay, the next question now is saying the terminal voltage of a separately excited generator decreases as the load current increases. So the instruction is saying, state two important reasons for the decrease in the terminal voltage, right? What causes the decrease in the terminal voltage of a separately excited machine is, number one, the voltage drop due to the armature circuit resistance, and two, the effective field flux is reduced actually due to the armature reaction as the load increases. So we are saying the armature reaction can also cause the decrease in what, in the terminal voltage, right? Let's quickly go to 3.2.1. Briefly state application for each of the following types of generators, differential coupler. So we just state one quickly, right? We can, it is used as welding generator or carbon arc searchlight. That's the differential compound generator. Then the series generator. The series generator is seldom used, but it can be used as a voltage booster on DC transmission lines. So it rarely has much usage. Doesn't have much uses. The series generator is a matter of fact. 3.2.3, right? Separately excited generator. It is used as a generator in the wide-Leonard motor generator system. We can use it in the wide-Leonard motor generator system. Right, we meet the wide-Leonard motor generator system in levels that are ahead in the calculations and stuff. But we know that it's one of the uses that the separately excited. So we should know that it's one of the uses that where the separately excited generator can be used for. Right, let's quickly go on 3.3. Question 3.3 is saying a 4-pole wave wound DC generator rotates 850 drives per minute. The useful flux per pole is 30 webers and the total number of armature conductors is 500. If the terminal voltage is 400 volts and the armature resistance is 0.25, calculate the generated EMF. So considering the information that we are having, which I always advise that you list the data that you are having, then after listing it, then you can see which formula is best suitable. So in this case, to calculate the generated EMF, we have to use the formula E is equal to 2P phi NZ over C times 60, where E is the generated EMF, P is the pair of poles, and phi is the flux, and the N is the number, speed in revolves per minute, and Z is the number of conductors, and C is the parallel path that we are having. For swerve is 2 and for lap is 2P. Okay, so we just substitute directly into the formula 2 multiplied by the pair of poles. Consider the information that we have. They said it's a 4-pole machine, so we divide that by 2 to make it 2, the number of pairs, multiplied by the flux, which is 30 milliwebers. So it's times 10 to the power of -3 milli, right? And the speed, it's 850. So multiply that by 850 times Z, the number of conductors. They say it is 500 conductors, right? Divided by C, it's wave wound. So it's going to be 2 multiplied by 60, right? If we punch that on the calculator, that definitely is going to give us 425 volts. So this part is answered, right? So we go to the next question, which is now saying calculate the armature current. Right? So armature current, considering the generator, E is equals to V plus IARA, the information that we are having, right? So making IA the subject, it means IA is equal to E minus V over RA. What has happened? We transposed V to this side. So we ended up having E minus V is equals to IA RA. Then we divided by RA. We ended up having IA being equal to that. So substituting what we have, it means 425, the back EMF that we've just calculated, right, minus 400. 425 minus 400 divided by RA, 0.25 that we have. So what is that going to give us? That will give us 100 amperes if we punch that on the calculator. So apparently this is what we now have. That's question number 3 for us. Let's go to the next question, number 4. If our next question, it's saying a DC shunt generator delivers a full load current. Question number 4 is saying a DC shunt generator delivers a full load current of 556 amperes at 300 volts. The armature and the shunt field resistance are 0.3 and 120 ohms respectively. If the no load armature current is 2.2 amperes, calculate the following. 4.1, the armature current and the shunt field current. Right, so directly in calculating the armature current, we need, and of course also the shunt field current. So we can just directly say shunt field current is just to create this, okay? Right, so shunt field is equal to V over R shunt. That's what we're having there, right? So what is our terminal, our voltage? We've been told that it's 300 volts, so we just say 300 divided by R shunt, which we've been given as 120, and that gives us 2.5 amperes. All right, that's our shunt current. Then wanting to calculate the armature current IA is going to be equal to, right, this being a generator we're talking of, so IA is going to be equal to IL plus I shunt, right? So taking that 56 plus 2.5, and that gives us 58.5 amperes. Right, that marks our armature current. Let's go to the next question. The next question is saying the three losses occurring in the generator. The three losses that occur in the generator are the armature winding copper losses, the shunt field winding copper losses, and the iron, friction, and windage losses. Those are the three losses that we need to calculate. Right? So let's start with the armature winding copper losses. So we start with the armature winding copper losses. Right, copper losses. Okay, they are given by IA squared RA. So they are equal to IA squared multiplied by RA. Right, so we've just calculated our IA there, the one we got is 58.5 squared, multiplied that by RA, which is 0.3, it has been given there, and that gives us 1026.675 watts. That marks our armature winding copper loss, the first one. Then we go to the shunt winding copper losses. Right, the shunt winding copper losses are given by, we can calculate them in two ways. We can say I shunt squared multiplied by R shunt, or we can say V multiplied by I shunt. We still arrive. So I will just choose one thing for the sake of time. So we can use the I shunt that we already have, which is 2.5 squared multiplied by R shunt that we have, which is 120, and we can still arrive, or V, I'm going to use this one, 300, right? That's our V, terminal voltage multiplied by 2.5, the shunt current, we could arrive at 750 watts. So I say that if we were to use I shunt squared multiplied by R, we're still going to arrive at the same answer. Right, so let's go to the iron friction windage losses. Okay, iron friction and windage losses. Right, that is going to be given by V multiplied by IA at no load. So we've been given the IA no load current, the no load armature current there. Right, so we can use that no load armature current to calculate the iron friction and windage losses, which are some of the constant losses that we are having. For 300 multiplied by, right, it will be given as 2.2 there. So we are calculating it, we get 660 watts. That's our iron friction windage losses. Right, let's quickly go to the next question. Our next question is now saying calculate the power output during full load. So when the output power at full load, so P out is the one we are calculating, is going to be equal to V multiplied by I load, the IL at full load. Right, so the full load IL, and that is going to be equal to, right, V is 300, that's the terminal voltage multiplied by IL, which is 56. and that will give us 16,800, which apparently is also in kilowatts. It is the same as 16.8 kilowatts, was to be correct to say that. Right, so that's P out. That marks 4.3. Let's quickly go to 4.4. Right, for 4.4, the question is saying calculate the power input during a full load. The power input during full load. So P power input is equal to input power, right? The only difference that lies between the input power and the output power are the losses. So if we say P out that we already have plus the losses, they should give us the input power. It's one and the same thing. So we can now add 16,800 that we just calculated plus the three losses that we have, which are 660. We did calculate them plus 750 plus 1,026.675. If we add them all, so we just punch that on the calculator, we get 19,236.625 watts. Right, we can write that in kilowatts to 3 decimal places. It can be written as 19.237 kilowatts, rounding off to 3 decimal places. It's gonna be one and the same thing as well. Right, so let's go then to 4.5. 4.5 is now saying the efficiency of the generator. Efficiency is the ratio between the output and the input expressed as a percentage. So we are to say efficiency for this machine is equal to P out over P in times 100. And apparently we have just calculated P out. We have 16,800 divided by P in is the one we also calculate 19,236.625. Right, so multiply that by what? By 100. So if we punch that correctly on the calculator, we're going to get 87.333 decimal places percent. That marks our efficiency. Okay, let's quickly go to the next question. Question number 5. Right, so on question number 5. Okay, the question is saying the alternating voltage waveform is a maximum value of 325 at a frequency of 550 hertz. Calculate each of the following: the time taken to reach a 195 of the form. We have to, so whenever we want to convert it, multiply by 180 over pi, which is the same as 57.3 degrees time. What we need to do now is we are substituting what we have. They said for it to reach 195 volts, so E, this one is the 195 that we've been given. So we can substitute 195 is equal to EM, the maximum voltage we have been given. They said is 325. So we can substitute E is equal to 195 is equal to 325 sine, right, that marks sine 2 pi. F, we have been given the frequency as 50, right, T times, right, remember it's in radians of, in order for our answer to come out, we have to convert this to degrees. How? By multiplying by 57.3, right? So it must be known that in order to convert the radians to degrees, we have to multiply by that, right? So we can therefore safely simplify this now. Divide by 325, divide by 325, and that will give us right, 195 divided by 325, that is 3 over 5 or 0.6 is equals to sine 2 pi f 50 times 57.3t, right? Then multiply by arc sine on both sides, so that we end up having 2 pi 50 times 57.3t is equals to arc sine of 0.6, right? So we have sine there, right? So apparently, remember, this is sine 2 pi ft 2 pi times 50 times 57.3. So it means we now have this. Then we divide both sides by 2 pi times 50 times 57.3. So 2 pi multiplied by 50 multiplied by 57.3 both sides. Divide again this side by 2 pi times 50 multiplied by 57.3. So it means T is equal to arc sine of 0.6, right, divided by 2 pi times 50 times 57.3, and that gives us our time in seconds. It's going to be 2.048 times 10 to the power of negative 3, which is the same as 2.048 milliseconds. Right, that marks our time there. Right, let's quickly go to the next question. The next question is now saying calculate the time taken for the voltage to reach its maximum value. Right, the maximum value is the one we have, which is 325. So it means E, right, is going to be 325. So if 325 is equals to EM is also 325, that's what it means. Sine omega T, which is omega is 2 pi F, right, multiply by 50, multiply by T times 57. So that's T times 57.3. Right, so we can then again divide by 325, so it's more or less repetitive. So basically the idea was to interpret what that statement really means. Right, so 1 is equals to sine 2 pi times 50 times 57.3 T. Right, so remember the reason why we are saying 57.3, we are saying so because we are converting from radians to what? To degrees. So we have that, which is going to give us 2 pi times 50 times 57.3 T is equals to arc sine of 1. Okay, this is what we have. Divide by 2 pi times 50 times 57.3, right? Divide again by 2 pi times 50 times 57.3, and that marks, that's going to give us T is equal to, so T is equals to, right, arc sine of 1 over 2 pi 50 times 57.3. That's going to give us 0.4999 6 times 10 to the power of negative 3, which is equal to 5 millisecond rounding off. So it's 0.05 actually, 5 times 10 to the power of negative 3. So it's 5 milliseconds having rounding of our figures to, as usual, to 3 decimal places. Right, 5.3. Let's go to 5.3. 5.3 is saying calculate the form factor. Form factor, as long as we talk about a factor, we're talking about a ratio. So which ratio is form factor? Form factor is the ratio between the RMS value and average value. So form factor is equal to ERMS over E average. So we need to first calculate ERMS. ERMS is given by 0.707 multiplied by Emax, right? That's ERMS for us there. So that's 0.707 multiplied by Emax, which we already have, which is 325, right? 325, and that gives us 229.775. right, to 3 decimal places, punching that on the calculator, right? We have ERMS. So what is the next? The next thing, we now need average value, E average. So we are now calculating E average. E average is equal to 0.3637 multiplied by Emax. So these are given formulas on the formula sheet. So 0.637 multiplied by 325 again, and what do we get? 207.025 volts, right? So these are our values. So we come with them. We simply substitute now into the formula 3229.775 divided by 207.025, right? And that will give us 1,1098,9011 for pointed on the calculator, which rounded off to 3 decimal places is going to give us 1,11. That's the form factor without units because it is a ratio of 2 voltages. So apparently that's what we get there. The next is saying the crest wheel between the maximum value and the RMS value. That's the crest factor now, right? So what are we going to get? Crest factor. So we are saying crest factor is equal to Emax, right, divided by ERMS, right? So that's 325 there divided by 229.775. We have already calculated that. So what do we get? 1,414,427. So that's 1.414 to 3 decimal places, right? Without units, that marks our crest factor. Let's quickly go to the next question. Question number 6 is now saying the parallel RLC circuit consists of the inductance of 6 millihenries and a 50 ohm resistor and a capacitor of 115 microfarad. This circuit is then supplied at 130 volts, 50 hertz. Calculate each of the following: the total current flowing through each branch of the parallel combination. Right, so we want the total current flowing through each. I highlight how this circuit really looks like the way it is right now. So this is how the circuit looks like. So I'm going to start with the capacitor there. We have the capacitor this side, and then what else do we have? We have the inductor. So I'm going to indicate the inductor in this way. So there is our inductor. Right, from the inductor, we have the resistor. They are all in parallel with an RLC circuit. So we have the resistor, that marks our resistor there. Then from the resistor, we now have our source, the supply. So that marks our supply now. That marks our supply there, right? It's AC. So we just put the symbol for the AC. So it's 130 volts, 50 hertz. There it is. And this is the resistor, 50 ohms. And this is the inductor, 60 millihenries, right? Inductance is measured in henries, by the way. And apparently that's the capacitance, which is in, we've been given there as 115 microfarads. So that's 115 microfarad capacitor there. So the instruction is saying calculate the current through each branch. So we want IC, the current through the capacitor, IL, the current through the inductor, and IR, the current through the resistor. So we can start with the current through the resistor. It's very much straightforward. How we're going to calculate it. IR is equal to V over R. That's the current through the resistor. So V is 130. As a matter of fact, all these components have the same voltage because they are all in parallel. So 130 divided by 50, and that is going to give us, punching that directly on the calculator, it's going to give us, that's 130, divide that by 50. That's 2.6, I guess. Okay, let's go to IC or IL. The next current with IR. We now want IL there. So IL is given by V over XL, where XL is the inductive reactance. Do we have it? No, we actually have to calculate it. So XL is given by 2 pi FL, right? So 2 pi, multiplied by the frequency we've been given as 50, multiplied by the inductance 60. Milli is 10 to the power of negative 3. That's what milli means. So it's good to know milli, 10 to the power of negative 3, micro, 10 to the power of negative 6, nano, 10 to the power of negative 9, and pico, 10 to the power of negative 12. So it's good to know them in case we may meet them, right? So what do we get there if we punch that? So that will give us 18.8495. So that to 3 decimal places is going to give us 18.85, right, ohms. That's our inductive reactance there. So we can now come with it and substitute V130 divided by 18.85, and that will now give us, punching that on the calculator, that's 6.897 amperes to 3 decimal places, right? So that's our XL. From there, we now calculate IC. IC again is going to be given by V over XC, and as it stands, we do not have XC, we actually have the capacitance. So we can use that to calculate XC, the capacitive reactance. Capacitive reactance is given by 1 over 2 pi FC. So substituting that, that's 1 over 2 pi multiplied by F, the frequency, which is 50, times the capacitance, which is 115 times 10 to the power of negative 6. That's microfarads. So it's 150 times 10 to the power of negative 6. Right? Punching that on the calculator, it's going to give us 27.679 to the decimal place ohms. Right? That marks our XC. Right? So we come to the formula 130. The voltage, mind you, all of them have the same voltage divided by 27.679. Right? So if we punch that on the calculator, it's gonna give us, that's 4.697 amperes. So we have the 3 currents that are in parallel, right? The next instruction, the next question is now saying calculate that's 6.2, the total current flowing in the circuit. Right? So to calculate the total current, we now use the phasor sum. IT is going to be given by, for the parallel combination, the square root of IR squared plus IL is the one bigger than IC, so we can say IL minus IC squared. So these ones, they depend with which one is bigger than the other, right? So we can then safely substitute what we have. So IR, we have calculated it, that's 2.6 squared, right? Plus IL, we have it, that's 6.897 minus IC, we have it, that's 4.697 bracket squared. And punching that on the calculator, it's going to give us, right, punching everything there on the calculator, it's going to give us 3.406 amperes. That marks our total current. So from there, we've answered this question. So we go to the next, which is impedance. Impedance is equal to V. So Z, the impedance, equals to V over IT. So now we have IT, the total current now. So we take that advantage and we say, what is our voltage? Our voltage is 130 divided by what is our current? Our current is 3.406. And that is definitely going to give us 38.168 ohms. That's our Z, the impedance there. Right. So this is clear. We go to the next question. The next question is saying, calculate the power factor of the circuit. The power factor of the circuit, right? So in calculating the power factor, PF is actually equal to cos phi, right? So cos phi is equal to IR over IT. Right? So we can just take that directly and say 2.6 divided by 3.406, and that will give us 0.763. Right? That marks our power factor. Right. Let's quickly go to the next. Question number 7 is saying, name the 3 types of power factors at which a circuit can operate, right? A circuit can operate at a unity power factor, a power factor of 1. It can operate at a lagging power factor. It can operate at a leading power factor. These are the 3 types of power factors that a circuit can actually operate in. Here comes a question is saying 3.7.2 is saying a 3-phase star connected load draws a line current of 21 amperes at a power factor of 0.65 lagging from a 440 volt 50 hertz supply. Calculate the following: the active power of the load. Right. Active power, it's a 3-phase as a matter of fact. So active power, which is the true power or the active power, it's given by, so we are saying active power P is given by, so it's P is equal to root 3 VL, the line current, multiplied by IL, the line voltage times the line current, multiplied by cos phi, which is the phase and the power factor, right? So if we substitute that to 3, multiplied by, we have already been given the line current, the line voltage 440, we've been given also the line current 21, multiplied by the power factor, we've also been given a lagging power factor of 0.8 or 0.65. So you can just take that and substitute directly into the formula. So that's 0.65 there, right? So punching that on the calculator, it's going to give us 10,402.697, right? Which is 10.403 to 3 decimal places kilowatts. It's marking our true power of the active power of the circuit. Then the next question is now saying calculate the phase voltage. Right. For the phase voltage, remember in a 3-phase supply, there is line voltage, there is phase voltage, but then this is a star connected load. So since it's star connected, the phase voltage, I'm gonna call it VPH, is equal to VL, the line voltage, over root 3. That's how we calculate it. So we say 440 divided by root 3, right? So it's going to give us 254.034 volts. That marks our phase voltage, right? Let's go 7.2.3. 7.2.3, the phase current. Right, phase current, apparently it's a star connection. So phase current IPH is equal to line current IL, which is apparently equal to 21 amperes. So that's 7.2.3 there. That's why you see it's a 1-mark question, because it didn't need much of thinking. We have to know that in a star connected load or in star connection, we happen to have the phase current being equal to the line current. Right, let's go to the next question. The next question now saying the impedance per phase. So in calculating the impedance per phase, we are going to use the phase voltage VP divided by what? By IPH. That's ZPH, the phase voltage. So that the phase impedance. So that's 254.034 divided by 21, right? So it's going to give us 12.097 ohms. That's our impedance then, right? We have dealt with question number 7. Let's quickly go to question number 8, right? Question number 8 is saying a three-phase star connected 3-phase step-down transformer has a delta connected primary and star connected load secondary. The phase line, the primary line voltage is 6.6 kilovolts and the secondary line voltage is 380 volts. Calculate the secondary phase voltage. That's our question there. Right, the secondary phase voltage, right? VPH, I'm going to call it that again for the good sake of not mistaking it for the VP, primary voltage VS secondary voltage. Nonetheless, it's not a problem. Even if you call it VP, just make sure that you know what you are referring to exactly. So VPH is equals to VL over root 3. Why? Because we are on the secondary side of the transformer, and on the secondary side there is a star connection. So whenever we have a star connection, VL is equal to root 3 times the VPH, where VPH is the phase voltage and VL is the line voltage. So for that reason, we are saying it's a star connection. We have to do that. So we can now directly say, what is our VL in this regard? Is 380 volts that have been given there, the line voltage. So we can say 380, right, divided by, right, root 3, right? So what do we get? 219.393 volts. That's our VPH there, primary, the secondary phase voltage, right? The next question is saying calculate the transformer ratio, right? Transformer ratio. That's the next question there, right? So transformer ratio, if we want to calculate the transformer ratio, we take the phase voltage of the primary divided by the phase voltage of the secondary, right? Remember, this is a three-phase transformer. If it is a single phase, it's fine. We just take the voltages we are having because they are already the phase voltages. So since it's a three-phase transformer, we take the phase voltages to create the ratio, the transformer turns ratio, right? So we need the primary phase voltage. Now it's connected in delta, which means the phase voltage of the primary is also equal to the line voltage of the primary, right? They are equal, these two. Why? Because both of them, they are in a delta connection. Therefore, VL is equal to VH, which is 6,600 or 6.6 kilovolts that have been given, right? So having considered that, we then create a ratio using the voltages, the two that we're having, 6,600 divided by 219.393. As a matter of fact, it's very good to know that since it's a step-down transformer, we expect the number of turns of the primary to be greater than the number of turns of the secondary because it's a step-down transformer, right? So dividing that, we are gonna get 30.083000172, which is to the nearest whole number 30s1, because remember these are number of tens that we are calculating, so we can't leave it in decimal as a decimal, so we have to round off to the nearest whole number. That marks our transformer turns ratio. So it must make sense as we look at the answer on our own that this is a step-down transformer. We expect the number of turns of the primary to be greater than the number of turns of the what? Of the secondary. All right, let's quickly go to the next question. Right, our next question is saying calculate the primary line current when the secondary line current is 500 amperes. Right, that's our question there. So number one, since this is now the secondary side, since it's connected in star, it means IL, the line current, is also equal to the phase current, which is equal to the 500 that we have been given there, amperes. Right. There are two ways in which we can calculate this question. I will just quickly use one, but explain the other one, what we could have done actually. Right. So we can use the transformer turns ratio, the transformer ratio, which says I1 over I2 is equal to, right, N2 over N1. That's what we can do using the turns ratio that we have been given. Or we can use the voltages. I1 over I2 is equal to V2 over V1. It's good to know that, right? So I'm going to use the last, right? So making I1 the subject. So I1, which one are we calculating? We are going to find the phase current of the primary. That's the one we are going to find. So we can call it IPH primary. That's the one we are getting there. So making it the subject, we, after cross multiplying there, we have I1 V1 is equal to I2 V2, and we divide that by V1, of course, divide that by V1, which is going to give us that is our formula there. So we are saying I1 is equals to I2 multiplied by V2 over V1. Right, so substituting that with the information we are having, I2 apparently is the same, the phase voltage, the phase current, which is the same as the line current 500, multiplied by V2, which we did calculate 219.393, divided by V1, which is 6,600, right? And that is going to give us okay, and on the line, root 2, 3 multiplied by IPH of the primary. So apparently that's the one we've just calculated, the IPH of the primary. That's the, if we do one that we have, we will end up having 28.788 amperes. That's now marking the line current of the primary. So we have answered that question there. Right, let's quickly go to the other question. The other question is now saying, name two methods used to connect a three-phase load. Right, a three-phase load can be connected either as a star connection or as a delta connection. You can connect it as a star connection. You can connect it as a delta connection. Let's go to question number 9. State two advantages of the damping mechanism. Right, it's very accurate. It's almost a uniform scale. We can say that as well. And also, it is well shielded from any stray magnetic field. And it prevents the point from oscillating. Those are some of the advantages that the damping mechanism has. And then those are the advantages actually that the damping mechanism have. So let's go to 9.2, the two disadvantages of the damping. What about its disadvantages? It is expensive. It is only suitable for use on DC supplies, and the control springs of the instruments limit the current to a few milliamperes, and the moving coil ammeters must be always used with a shunt resistor. Those are the disadvantages that it actually has. Let's go to 9.3.1. A galvanometer has a resistance of 120 ohms and a full-scale deflection when 6 milliamperes passes through it. Calculate the value of the additional circuit component required to enable the instrument to be used as a voltmeter capable of measuring between 0 and 6 volts. Right. For a voltmeter, we are saying this is the situation that we have. This is the situation that we have. I'm answering 9.2.1. So we are saying this is what we are having. Right. Number one, we need to know that to calculate R series, it's equal to R1 minus Rm, because R1 is equal to R series plus Rm. Right, the series resistance plus Rm. Right. If that is the case, then how do we calculate R1? R1 is now equal to V over I. It's actually V1 over I1, but I1 is also equal to Im, so we can safely say V over Im. Right, so we take our voltage in order to calculate R1, 6, that's our maximum there, divided by, right, Im, which is 6 times 10 to the power of negative 6 multiplied by 10 to the power of negative 3. Right, so this is what we have. And that is going to give us 1,000 ohms. That's R1 apparently. Therefore, it means it's possible now to calculate R series. R series, the resistor that we need, is going to be equal to 1,000 that we've calculated. That's our R1, mind you. Right, minus Rm, which is 120. So 1,000 minus 120, that's 880 ohms, which is the same as 0.88 kilo ohms, if we want to express it that way. That's our resistor that is needed for the machine to act as a voltmeter. Right, so the voltmeter capable of measuring that. That's we've just calculated the size of the resistor. Let's go to the ammeter. Right, on the ammeter, an ammeter to measure up to 2 amperes. Right, on this is the connection we actually have. All right, of course, that's what we have. We are having there, and the resistor is now connected here. There it is. So there's one key information that we have. Okay, so something like that. Pardon me, my diagram is a little bit weird. Let me just try to correct it here, just here, just at this part, right? So this is what we have. This is what we are having. Okay. Right, so we have our shunt, the shunt resistance here, and we are saying this is our machine to act as an ammeter. Right, one key thing to take note of, we have RM again here, right, and then we have I shunt going towards this direction, we have IM going towards this direction. Since these two are in parallel, V shunt is equal to VM, that's the key, which means I shunt, R shunt, that's the formula for V shunt, is equal to IM multiplied by RM, right? Making R shunt the subject, that's the resistor we want, it's going to be equal to IM times RM over I shunt. As it stands now, we do not have I shunt, but we have the current I. So it means I shunt can be calculated. It's equal to I. So for I shunt, we are saying it's equal to I minus IM according to Kirchhoff's first law, right at this junction here. Right. So for that reason, we are saying our I is 2 minus IM 6 times 10 to the power of negative 3, and that will give us 1,994 amperes. That's our I shunt there. So it means we can now come into the formula and substitute 6 times 10 to the power of negative 3, that's our IM, multiplied by 120, that's our RM, divided by 1,994, that's our I shunt, which is going to give us 0.361 ohms. That's our R shunt there. So we have answered this question. Let's quickly go to question number 10. Question number 10 says 10.1. Determine the number of possibilities for the following. Number 1, an 8 input gate. So n is equal to, you just have to say 2 exponent of the input that you are having, right? So in our case, it's 8. So 2 exponent of 8 and 2 exponent of 8, that's going to give us 256 combinations. So it's having 256 possibilities or 256 combinations, right? And then it means even the 4 gate. So we are saying these are 256 possibilities that we have, or combinations that we have, right? And then for 4, we are also saying 2 exponent of 4, which is going to give us 16 combinations, right? These are the possibilities for these two situations that we have, 8 input and a 4 input gate. Determine state, so 10.2, the 4 characteristics of a common base circuit, right? Number 1, it has a high value of gain. 2, it has a low input impedance or high output impedance. It has a current gain which is less than 1, and it also has no invasion of the signal, which means there is no phase displacement or phase shift that is going to occur, right? That's 10.2 characteristics of the common base circuit. At 10.3, use binary subtraction rules to subtract the following binary numbers. So I want to subtract these numbers. So I want to demonstrate on this question, how does an example subtract the decimal numbers? I'm going to give a simple example here of 24 in decimal minus 9, the ordinary numbers we know of, right? So let's subtract 4 minus 9. So we say it's impossible. We usually just say 1 and put a 1 here if that is the method the giving method. I'm not using the taking method of taking a 1 here, putting it. I'm using the giving. So take a 1 here, give a 1 there, give a 1 there. So that's 14 minus 9. It's now 5. Then, of course, 2 minus 1 there, that's a 1. That's what we do. So what were we doing? What are we doing actually? What we are doing is we are saying we are in base 10. That's our base. That's the decimal. So we say the 4 minus 9 is impossible. Therefore, we gave a base 10 here. And we say 10 plus 4. So that was not just an ordinary one we were placing. It was a 10. Why? Because we were in base 10. So 10 plus 4, that's 14. So that's where the 14 came from. So we said 14 minus 9. Now we are getting a 5. Then instead of, after giving the base 10 here, we gave a 1. Already we know that it's representing for the decimal values that we already have. For right, so it's going to be 2. The units that we already have, tens are units, tens, hundreds is as we are going. So it's 2 minus 1 here. It's going to give us a 1. So our answer is 15. So let's go and really exactly replicate that on the binary number that we are having there. Right, so the binary numbers that we have, let's replicate the same thing. Right, let's take them. It's 1. Okay, so just try to clear my screen there, right? So our binary number is 1, 1. Okay, it's 1, 1, 1, 0, 1, 1, 0. Right, subtract 1, 1, 0, 1. We need them to be corresponding. So that's base 2. That's base 2 there. Right. So that's 0, 1, 1, 0, 1. Exactly. That's 1, 1, 0. Okay. So there are our numbers. Right. So let's subtract. We are subtracting, remember. 0 minus 1, it's impossible. So we give a base here. We are in base 2. We give a 1 this side. So you give a base, you give a 1 there. So 2 minus 1, that's a 1. 1 minus 2, this is no longer a 1, it's now a 2 because we gave a 1 there. So 1 minus 2, it's impossible. We give the base again here to add it to the number that we already have. We're adding it. So we say 2 plus 1, that's a 3. 3 minus 2, that's a 1 again there. Right. 1 minus, so we said we gave a 2 here. We are going to give also a 1 this side. Right. Give a 2, give a 1. 1 minus 1, that's a 0. It's fine. 0 minus 1, the next one, it's impossible. We give again a base, we give a 1 this side. So 2 plus 0, of course, that's a 2. 2 minus 1, that's a 1, right? 1 minus 1, that's a 0. So our answer becomes 1, 0, 1, 1, base 2, right? We have subtracted in binary. That's how we perform the binary subtraction. Right, so basically this is what is happening. This is marking the end of our revision of the Electrotechnology N3 paper that was written in August 2024.